Okay, so let's restart. So we did this, monstrous looking calculation, but it was with a goal. Is now what we showed is that once we restrict y to taking only two values, satisfying still those constraints, then the value that we get on that quadratic form is exactly this normalized cut. Right? So what does this mean? Right? Now we can collect all this work that we did. Right? What does this mean? This means that lambda 2, and this is really the important thing, right? This is equal, as we saw just before, as the minimum, right, over y satisfying y transpose y being 1, y transpose d1 being 0, the sum over I and j, yes, edges, yi minus yj squared. Now, of course, this is smaller or equal than if we take it the same thing exactly, but forcing it to be to take only two values, right? So y now needs to be of the type ab to the n for some a and b, right? So I'm asking for more, right? I'm minimizing over a smaller set, so of course the minimum is bigger. This is equal to the minimum, right, over s, right? And this is really the important. So the important part is really all here. S over volume of S plus cut of S over volume. Okay, it's really all here. Okay, so this is the proof of the theorem. Okay, now we did more than prove the theorem. Right? There's a few. There's two. I mean, there's maybe more than two, but there's at least. I guess let me talk about what there's one very important implication of this thing that we just proved, right? Which is if we wish to cluster a network. So let's say that we want to cluster a network, cluster a graph, right? We want to find communities of a graph. Okay, we can ask that we want to find, right? We want to find S and S complement partition, right, with small normalized cut, for example. Right, so let's say that this is an algorithmic goal that we have, which is a very common algorithmic goal. Yeah. Right? It's one of the most. I mean, we saw k-means as an algorithm to cluster data, right? But in a graph, this doesn't quite make sense. And then we saw how if the data doesn't split linearly, we can try to create a graph out of it, right? Or at least maybe a weighted graph using the kernels. And I should say that everything I'm doing works just the same for weighted graphs. I'm just trying to lighten the notation to not add weights. But let's say that we want to cluster a graph. Then what does this mean? This means that what we want to solve is we want to optimize this thing, right? Let me call this sharp, right? We want to minimize this expression. However, minimizing sharp is hard. Right? It's computationally hard. Right? It's in fact NP hard. Right? It's not so hard to believe, right? You're like finding the minimum balanced cut of something. These things tend to be NP hard, right? I don't want to talk much about complexity. It's just we don't expect to be able to do it efficiently. However, minimizing this one, exclamation point, exclamation mark, is easy. Right? Why is it easy? Because, I just take, I can just take Z, I can just compute eigenvalues and eigenvectors, right? And this I know how to do, right? So that's of course much easier, right? I can just, why is it easy? Okay, let's be more specific. Take compute Z being the second eigenvector of LG, right? This is a spectral problem, okay? And then take Y equals D to the minus a half Z. It's as hard as computing an eigenvalue eigenvector problem. Okay? If by chance we do this and we get something that only takes two values, then we know that indeed we must have found the cut that minimizes the normalized cut, right? We must have found a partition. However, we're not always going to have this happen. And so this is the key idea of what's called a relaxation, right? So this is the key idea behind the relaxation. And it motivates an algorithm. Okay, what is the algorithm? Okay, so let me give you the algorithm. Okay, okay, so this is the idea of relaxation. Let's give an algorithm. Let's say algorithm for finding good partitions. Okay, so what's the algorithm? Okay, here's the algorithm. Compute y minimizer of formation mark. Should say this is a spectral problem. Okay, now this unfortunately will not have only two values, so you need to round y. What do I mean by round y? I grab the entries of y and I say, I look the small ones I make it be set s, and the big ones I make it be s complement. Okay, the word rounding comes because this was traditionally used in integer programming, where you have to optimize things over integers, you relax them to not be integers, and then you literally round. Here we still use the word rounding, but how would I do this? Is I would say, right, so what I mean by given round this is given a threshold, right, given a threshold, tau, just define S equals all nodes I such that yi is smaller or equal than tau. Okay, and there's many ways that you can do this. You can just try all of them. Okay, you would think trying all thresholds seems like ridiculous because, there's infinite possible thresholds. But really, if a threshold is in between two values of y, then it gives the same thing. So all you have to try is all possible ways of splitting, right? The entries of y, you order them in the real line, and you just have to find all ways of splitting. So this is actually efficient. Trying all of them is easy. Or you can just use two means, or use k-means for k equals 2, right? On the values of the entries of y. Okay, this seems now like a very simple algorithm, right? Certainly is very well motivated by the things that we described. And this is the idea of a relaxation, relax and round type algorithm. They're very popular in many fields, including computer science. Okay. So this algorithm has a name, and this algorithm is known. This is known, which probably you've heard before. This is known as spectral clustering. It's one of the most popular algorithms to cluster graphs, or even data, right? Because from any data set, I can make a graph by connecting points that are nearby. Okay, now there's a few things that I can say, but I wanted to tell you a little bit about finite frame theory, at least give you the definitions, because it's mostly just giving you the language, but I still wanted to do that today. there's now many ways in which we can. There's many questions that I think get brought up from this, right? And I'll answer some of them. Some others are out of the scope of this course, but I put some references in the notes. Right. One is, are there guarantees for it? Can we guarantee that actually with this rounding step we don't lose too much? And so indeed there is a guarantee, and this is basically what Cheeger's inequality says. Cheeger's inequality essentially, so you should look at the notes to see like to get it exactly at the right constant, you should define something which is the Cheeger cut, which is just like the normalized cut up to a factor of 2. So that the inequality looks nice in the way that you'll see it in books if you go look it up. But basically what it says is when you do this, right? So when you do this, the cut produced by this. So basically it says that there exists, okay, that there exists a tau, right? A threshold. And remember, you can try all of them, so it's a guarantee for these kinds of things, such that the the cut that you get, right, such that the cut of S, okay, maybe I should write here S tau, okay, such that the cut of S tau, now instead of doing the times 1 over the volume and 1 over the volume, the complement, I'm just going to divide by the minimum, right? This is the same up to a factor of 2, but it's somehow nicer to do it this way. Okay? Such that this is smaller or equal than square root of. Okay? And so this is known. This is proving this is outside of the scope of this course. But this implies something that's known as the hard side of Cheeger's inequality. Okay, so let me just show you Cheeger's inequality because it's a really nice theorem. So I showed a proof of this in my more advanced class that I'll teach next fall if any of you is interested. So Cheeger's inequality will say that, okay, so let me define this notion of the Cheeger constant, which is the minimum. It's like the normalized cut up to a constant of 2, minimum of S of cut of S is divided by the minimum of the volumes. Okay. So clearly, right, clearly, I mean, maybe I should say, right, so clearly this quantity, right, is right, end cut is for sure bigger than this because I take, right, because I take cut over one of them plus cut over the other. Here I'm just picking the biggest of those two terms, and is smaller than 1/2 times end cut. Okay, just that to write this inequality, it's nicer with this expression, but they're the same up to a factor of 2. Okay, and Cheeger's inequality says the following. Says that in the definitions above we have the following. So this is one of the nicest theorems in spectral graph theory. Right? We proved this. Right? We proved. This is called the difficult side. It's not that difficult, but it would take a whole 2-hour slot. But see, okay, why did we prove this? Because of this relationship between this quantity and the end cut, right? They're the same up to a factor of 2. we prove that n cut is bigger than the eigenvalue, so it must be bigger than 1/2 of the eigenvalue because of this relationship with the factor of 2, right? Don't worry too much about the factor of 2. And basically this guarantee here, right, will give the fact, gives this side, gives the difficult side. Okay, so in the notes I put references to the proofs if you're curious to go read. There's many different proofs of this fact. This theorem dates back to the 70s. It was first understood in differential geometry, in manifolds, not in graphs, and then it was adapted for graphs in the mid 80s. Right. So Jeff Cheeger proved this for manifolds. Actually, his goal was a bit different. Right. So in manifolds, he was interested in understanding what do the eigenvalues of the Laplacian in a manifold look like. And things like cuts are things that are a bit easier to understand, and so this way he gave a relationship. Right? The interest from the viewpoint of spectral graph theory of algorithms is more that we cannot compute these cuts, but eigenvalues we can compute. Right? And so sort of eigenvalues are the easy thing computationally to understand and cuts not. And so sort of the interest comes from the other side, but in fact, but the inequality is exactly the same for manifolds. And even the proofs are very, very similar. Now, another thing I want to mention before we move to more linear algebra type things is you can, and a very another natural question is, what about more clusters? Right? What about K clusters? Okay. So for K clusters, there's also a spectral clustering, and it follows exactly the same thing. Okay, so I'll just describe the algorithm very, very briefly. But basically, you define, right? You take the one thing you can do is you can take, right? You can take V2, let's say V2, Vk, the eigenvectors of, so this would be the eigenvectors of the Laplacian, or corresponding to the eigenvalues, of course, lambda 2 and all lambda k, right? And now you take, right, and now you take, let me call them phi, say j equals d to the minus 1/2 d to the minus 1/2 vj. Okay, so now the phi 2 would be y, but other phi's, will be like corresponding to the third eigenvalue, fourth, and so on. Okay, and now you do the following. You take node I, so node I, we represent it. Okay, so think of this as a representation in the following way. Right, remember, the first eigenvalue is very boring, right? Because it corresponds to this whole one's vector. It says nothing about the geometry. Phi 2 entry y of this vector, phi 3 entry y of this vector. Okay, take this representation and then do k-means on this representation. Right, and that's it. This is spectral clustering. Okay, if you've ever used spectral clustering, just used as downloaded some codes to cluster some data. Chances are they use some form of spectral clustering. This is exactly what they did. Okay? And there are guarantees for it, very like a higher order Cheeger's inequality. Although there's lots and lots of open problems related to that, like very interesting open problems. If you go, I reference some lecture notes where I have a big list of open problems. But there's another key idea here that I think is worth mentioning, which is that this representation might not just be good from the viewpoint of doing clustering. It's also a way to represent a network, right? It gives you a way of representing, right, a graph in Euclidean space, in this case, k minus 1. Okay? So this has a few different names. Okay, you may have heard some of them. sometimes this is called diffusion maps. Sometimes this is called um, Laplacian eigenmaps. Sometimes some of these are like normalized in slightly different ways. Instead of taking the d to the minus a half, you might do something else, but they're all essentially the same. Sometimes it's called as a spectral embedding. I mean, I'm now, these things for large K and so on, I'm just giving you in case you're interested to be able to go look up these things. And now, as think about it at home. Think about the relationship of what we discussed with kernel PCA, right? When we talked about kernel PCA and truncated SVD and so on, right? It's exactly the same thing, right? We're taking the eigenvectors of this Laplacian and we're using them for coordinates of our nodes, right? They're the smallest eigenvalues because L is like something minus the adjacency matrix, right? So it works like as a symmetric of a kernel in a way. But this is exactly the same as these types of kernel PCA that we saw. Okay? And this is exactly what's behind spectral clustering, right? And you saw the kind of math that shows up. I mean, it proves that theorem precisely. And then, unfortunately, to prove Cheeger inequality, we need a lot more time. But yeah, I give references in case you're interested, and I'm happy to stop by. I offer office hours almost every day. Stop by. I'm happy to tell you more about the proofs of this. Okay, so I'm going to now talk a little bit about finite frame theory, just the very start, and yeah. So if there's any questions, I'm happy to answer any questions. Otherwise, I'll start with frame theory. We're just going to see the definitions today. Okay, if there's no questions, then I will start. So done with graphs for now. We're going to start talking about parsimony and about sparsity, low-rank structure that will be important for recommendation systems and so on, but it'll be very useful to have a certain language. And so it will be useful to develop this finite frame theory, the theory of sort of overcomplete dictionaries in finite dimensions. Okay. So I'm going to do things over the complex numbers, but it's this exact same thing doing it over the complex numbers or the reals. In fact, in the lecture notes, I just did it over a field K that you then should replace by reals or complex, depending what you want to do. Okay, well, let's say that we have vectors, phi1 through phi d. Say phi1 through phi d, vectors in CD, right? Complex valued d-dimensional vectors. Okay, it's the exact same thing for reals. It's a bit richer and okay. So right, if x is in CD, right, one can represent x via these coefficients, right, via the inner products. You can also, of course, represent it via the entries. But the thing is, maybe I should say this, the thing is that this theory is particularly important in infinite dimensions. Right, it's important there to be an inner product, so it's in Hilbert spaces. And so this theory is very nice in infinite dimensions, but actually you're going to only need the objects for finite dimensions. But so some things might seem like a bit of an overkill, but it's because this theory is all developed for infinite dimensions. If this is something you're interested in and you have some background in functional analysis, you should definitely go take a look. But we're going to restrict to finite dimensions, so you don't even really need to know what a Hilbert space is. Okay. So okay, so we can represent via these vectors bk, right? So if phi1 through phi d is a basis, then this representation is unique, right? We can go back and forth. Moreover, if phi1 through phi d are an orthonormal basis, then we have a form of stability. We have basically what's called a Parseval identity, right? Which is that the norm of x squared is the same as the norm of the square of these bk's, right? Usually the way we would write this is, so k from 1 to d, right, of right? And so now, right? So if you, okay, this seems like the norms are the same, but if you do it for x being like the difference of two vectors, say y minus z, right? Then it shows that if your representation is very, very close to each other, if the coefficients of your representation are very close, then the vectors also need to be very close, right? So if you replace by this, you get a sense of stability of the representation. Okay. So now there are many cases in which it's very useful to have redundancy. Like, maybe I'm not going to motivate this too much, but I should maybe just say that this is very useful in, for example, signal processing and communication, right? Which is that to take not just a basis, but to take phi 1, phi m in CD with m potentially bigger than d, right? And here what we're going to want is that they span, right? The span, they should be, their span should be the whole thing, should be equal to CD, right? They should span the whole space. What are the advantages of this? There's many advantages. It gains some form of stability and so on. But in particular, if I want to communicate, right? If I take these beta k's, right? If I have a signal x, okay, and now I go and I compute, represent x via these beta k's. Then I send beta k's through some communication channel. Okay, so I send this to some kind of communication channel. Then redundancy allows that if some, if say, if say for example, if of one of the beta BKs is lost, is erased, say in the channel, right? Sometimes communication channels are noisy or they may erase things. It still may be possible to reconstruct X, right? Right? If I have many, many vectors, if I have, say, two bases, clearly if I lose one element, I can just use the other bases to represent. So here's an example. Let's take b equals 2. Okay. And let's take this frame. Right? This is known as the Mercedes-Benz frame. So let's take this frame. And now, let's say I want to send a vector x. I send the inner product against each one of these frame elements. Okay, I haven't defined what a frame is, but it'll just be the name I give to these vectors, right? But these three vectors, right? And so I have a vector x. I compute, the inner product of x with phi 1, x with phi 2, x with phi 3. It's clear that any two inner products is enough to reconstruct x, right? Any subset of two will span the space. So any two coefficients are enough to reconstruct x. Okay. So this is why one would consider overcomplete. So these objects are sometimes, I should say maybe, they're sometimes called overcomplete dictionaries. The reason why we're going to want them is a bit different, but this is easier to or sometimes redundant dictionaries. And all this that I'm going to say makes perfect sense in infinite dimensions. Although for the sake of this course, that doesn't matter, just in case you're curious to learn more. Okay. So now comes a few definitions. So now we want to understand how good such an object is. In particular, we're going to want right? Of course, if I have something that's not an orthonormal basis, I will not have a Parseval equality. But what I want is I will require some form of stability. Okay, this is the last thing of intuition, and then I'll give the definitions. Right, and I want a close to a Parseval identity. So what I will want is that phi kx, or am I using phi kx or x phi k? X phi k. I guess not quite the same because they're complex numbers. Doesn't really matter. Right? I will want that this will not be exactly equal to x, maybe sometimes, but not necessarily. But I will want that this is up to constants is close to x. Okay, so let's now see a few definitions. Okay, and now I mean we're mostly going to just have definitions. So phi 1, and I'm using them over the complex numbers, but it's the exact same thing over the reals. CD is a frame of, I mean, we can say a frame of CD or in CD. Let's just call it a frame. If and only if there exists A and B, right? Of course, this should be smaller than infinity, and this should be smaller than 0, such that for all x in CD, we have that so you'll prove in the homework, right? It'll be in the homework that frame is equivalent to spanning set. I should say finite frame. So the situation is much, much more delicate in infinite dimensions. And this is related to stable sampling theorems for signal processing and lots of interesting stuff. But here it will be equivalent to spanning set. We'll prove this in the homework. But still, it will be quite useful to have this language nonetheless. Okay. So A and B, okay, well, let me say, so A and B are known as frame bounds. Frame bounds. Right? So the best possible, like, right? So if A is a frame bound, anything smaller than A is of course also a frame bound, but we'll call the optimal frame bounds just the best possible ones. Right? Because it's a spanning set, we also clearly get that n is bigger or equal than D, otherwise it can't possibly be a frame. Okay. Okay, so now there's a few definitions. So it's useful to consider, I'm going to use a little bit of abusive notation, and I'm going to, like, I use the notation for a matrix and for the operator that the matrix represents, and I'll use it by the same letter. We always do this, but a little bit of abusive notation nonetheless. Let me build the matrix. Right, so this is the D by M matrix. Okay. And now there's a few names. These three names are not maybe so important for finite dimensions, but it wouldn't be right for me to tell you about finite frame theory without giving these names. So this operator from C to the M to CD is called, people in frame theory call it, it's called the synthesis operator. The adjoint of it, right? So the adjoint operator, CD, CM, right? Maybe I can write a bit what is it's just the operator given by the matrix, right? So what is this operator? Phi of a vector, so phi of a vector C is equal to sum of of CK phi K, right? The adjoint operator, it's not the inverse, it's the adjoint, is called the analysis operator. I mean, these names are really not so important, but if you ever decide to pick up a book on frame theory, You'll find it strange if I don't tell you about them before. Right? So what is this operator? This is just a transpose, right? So given a vector x, it gives you the list, right? It will give you the list of the inner products. Yeah, x. Okay. Okay. Now, and then there's another one, S, which is the self-adjoint operator. So it's the operator between CD. Of course, the finite dimensions are only matrices. And the given by S equals phi transpose. It's just a Gram matrix. It's called frame operator. Okay. Okay. Now maybe more interesting statements. Okay. So easy things first. This frame operator, right, the self-adjoint matrix, is positive semi-definite, right? It's of the form phi times phi transpose or phi conjugate. So of course it's self-adjoint, and S is invertible. Okay, this is worth trying to prove. This I leave as a challenge. This is worth trying to show that S is invertible as a matrix. Right, but I mean, it's kind of clear probably to you already that, right, you're taking phi times phi star. If you think in terms of SVD, it's just saying that these phi's are full rank, right? And then it's not so hard to imagine that full rank will have something to do with the phi spanning the set, and the frame needs to span the set, and that's basically the proof. Okay, now some cool definitions. Okay, so a frame. Okay, so more definitions. Sorry that today we have is just setting up language. Um, okay, so these now four definitions are important. But they're also very natural. While the other ones are just like the names sound a bit strange, these ones are very natural. So a frame is said to be tight if and only if A equals B. Right? The frame bounds are exact. Right? So a frame is tight if the Parseval equality is an equality, or maybe up to a constant, like maybe A and B are not one, but if this is right, if the L2 norm up to a constant, but the same constant, the L2 norm of the vector is the same as the L2 norm of the representation. Okay. Okay. A frame is said to be unit norm if and only if this one is pretty easy. Like K is norm one for all K. And then a frame is said unit norm tight frame if it satisfies both properties, right? Those are particularly interesting objects. Okay, now there's our two other definitions. So far they seem a bit arbitrary. Then the next ones are going to be pretty interesting. Okay, and so remember this notion, this idea of erasing, right? So I erase a bunch of things and I stay with whatever many I didn't erase. I still need those to span the space, right? And so this comes in this notion of spark, right? And so the spark, so if any of you has studied matroid theory, this is a very important, it's related to the girth of the matroid and so on, but here is a simple thing. So the spark of a frame, phi 1 through phi m, is, is the minimum k for which there exists a subset S, subset of the frame elements. Right? What I mean by this m inside the parentheses is just the numbers from 1 to m, okay, of size k, such that phi I, the set phi I, is linearly dependent. Okay? So it's the smallest possible set you can get such that these vectors are linearly dependent. Okay, so I think 5 minutes, so easy thing to see. The spark is smaller or equal than the dimension plus 1. Right? If I grab d plus 1 vectors in d dimensions, for sure they're going to be linearly independent. They're going to be linearly dependent. Sorry. Right? So, I mean, I can make this proposition. Shouldn't be raised to the level of a theorem. Proposition: spark is smaller or equal than d plus 1. Proof: just any set of d plus 1 vectors in d dimensions is linearly dependent. Right? Basic fact in linear algebra. So for sure, if I take d plus 1, then I'm going to be linearly independent. And so we can call a frame, if it has spark d, we can call it full spark. Right? It's a bit different than full rank. Right? Full rank says that they span a subspace of like if I have, let's try to get a bit of right, some intuition now. I like think of this short fat matrix, right? This matrix is short fat, right? Because we think of m bigger than d. Being full rank is saying that there are d vectors that span the whole space. We can pick d columns that span the whole space. Being full spark is saying that for any d vectors, they must span the whole space. It's a much stronger statement, right? It feels much more combinatorial, right? In particular, computing the spark of a matrix is very hard and is NP hard, while computing the rank is something very simple. Okay, so last definition for today. Okay, and then we're going to start. These definitions are going to come back in the theorems, and I mean, I'll remind you of them, but I just want to give you sort of the objects that they're going to be at play. Right, another definition. So this one makes most sense for unit norm type frames. So um, the worst case coherence of a unit norm frame is mu equals the maximum for all, say, k different than L of the inner product of phi k, phi L. Okay, so 1 minute of intuition of why this definition is important. And again, it's not important for you, of course, to remember these definitions. I mean, whenever they show up, we'll recall them. But just for you to see the kind of objects that are going to start showing up, just to try to get some intuition, right? Keep in mind this Mercedes-Benz frame, right? It feels very much like they're sort of at the biggest possible distance between themselves, right? And in general, make a lot of sense to try to pack vectors in very high dimensions, a lot of vectors in less dimensions than a number of vectors, like m vectors in d dimensions with m much bigger, in a way that no two vectors are very close to one another. But if all the vectors are norm one, then the distance basically has to do with the inner product. So by making sure that all the vectors are a very small inner product, it makes sure that all the angles in between these lines are all very large. And so getting a control on the worst case coherence is basically getting a control in how close to each other are the two frame vectors that are closest as possible. Right? And so a good redundant system will be a system in which this is small, right? In which the spark is large and this is small. And in fact, there is a relationship between the two quantities. Right? So we'll want, so the goal will be to make mu small. And there's like a lot, you know, now, although the definitions of frames and so on don't make a lot of sense I mean, They make perfect sense, of course, but they don't seem so consequential in finite dimensions because, right, it's just a spanning set. I mean, these are just matrices and their transposes, right? They're not really, we don't need to think of them as operators or anything. These notions now make perfect sense and they're already very interesting in low dimensions, right? I give you I give you a budget of m vectors in d dimensions. What is the smallest possible coherence you can get, right? This is a very interesting packing problem now, right? And so we're going to, it turns out that this packing problem will be related to being able to perform sparse recovery and recover vectors, sparse vectors from linear measurements. And all this will motivate a certain algorithm for recommendation systems in the matrix completion. So we'll see all of that throughout the next 2 weeks before the break. Okay, thanks so much. Sorry for the extra minute, and I'll be happy to stick around if there's any questions.